The second derivative also serves as a test for concavity and to find points of inflection. Let's take a look at some concavity. Here we have concave up. It can also be recognized as a smile or as a bowl faced up. Here we have concave down. This can be recognized as a frown or a little bowl face down. The exact point where the concavity of the graph changes is the point of inflection. Consider the following graph. Here the graph is concave down, and here the graph is concave up. Suppose that at this point the slope of the graph is 6. And as we move up, the slope of the graph is decreasing, and here it's 0.5. Therefore, f prime of x, or the first derivative, is decreasing. Over here, suppose that the slope of the graph is 0.2, and f prime of x, or the first derivative, is increasing, and here it is 10. This is why the second derivative test for concavity works, because it's the slope of the graph either increasing or decreasing, which indicates where the graph has concavity upward and concavity downward. And this point here is the point of inflection, because it's the exact point where the concavity of the graph changes. Let's try a problem now. Given f of x is equal to x cubed minus 6x squared plus 12x, find the points of inflection and discuss the concavity of the graph. First, you have to find the second derivative. So first, write out the given function and take the first derivative. And the first derivative is going to be 3x squared minus 12x plus 12. Now we take the second derivative. The second derivative is 6x minus 12, which can also be written as 6 times x minus 2. The second step when determining concavity and points of inflection is to set the second derivative to 0 in order to find possible points of inflection. So setting it to 0, we find that a possible point of inflection is x equals 2. Now we have to test it, and the way that we're going to test it is by doing the third step, which is creating intervals based on the possible points of inflection and then testing them for concavity. So let's go ahead and make our chart to set up our intervals. We're going to set our intervals from negative infinity to 2 and from 2 to positive infinity, because those are the correct intervals built around our possible point of inflection. Because negative 1 is in between negative infinity and 2, negative 1 is going to be our test value for the interval negative infinity to 2. And for the interval 2 to positive infinity, we're going to have the number 3 be our test value, because it's in between the given interval. Now we test for the concavity. The second derivative of negative 1 is going to equal to negative 18. Therefore, the second derivative is less than 0. When we test the second derivative at x equals 3, we get 6. Therefore, the second derivative is greater than 0. This implies that on the interval from negative infinity to 2, the graph of the function is concave down, and from 2 to positive infinity, it is concave up. Because the concavity indeed does change at x equals 2, you can conclude that x equals 2 is going to be the x value for the point of inflection. So now that we know that 2 is indeed a point of inflection, the fourth step is to test for the actual point by plugging in your x value, in this case x equals 2, into the original function. If the original function was f of x is equal to x cubed minus 6x squared plus 12x, we're just going to go ahead and plug in 2 into that to get our point of inflection. Be careful not to plug in 2 to the second derivative. It's a common mistake to plug it into second derivative because that's what we've been working with, but no, you have to plug it in to the original function. So let's go ahead and plug in 2, and now we find that we have the point 2, 8, and that is our point of inflection. Let's take a quick look at the sine graph. From 0 to pi, the sine graph is concave down, and from pi to 2 pi, it is concave up. And because of this, we can determine that on the interval of from 0 to 2 pi, the point of inflection is going to be located at pi, because that's where the concavity of the graph changes. Now let's go ahead and try a trig problem. Given f of x is equal to sine x plus cosine x, find the points of inflection and discuss the concavity of the graph. First, as we did before, let's write down our function f of x is equal to sine x plus cosine x on the interval of 0 to 2 pi. Now we take the first derivative. That's f prime of x is equal to cosine x minus sine x. Now let's take the second derivative. F double prime of x is equal to negative sine x minus cosine x. Our second step is to set it to 0. F double prime of x is equal to negative sine x plus cosine x is equal to 0. Negative sine x is equal to cosine x. Now we know that the second step is to set it to 0. So f double prime of x is equal to negative sine x minus cosine x. Now let's set that to 0. Negative sine x minus cosine x is equal to 0 gives us negative sine x is equal to cosine x. Now we can determine that x equals 3 pi over 4 and 7 pi over 4 are going to be our possible points of inflection, because that's where sine and cosine values have the same value but different signs. Now our third step is to set up our intervals. So let's go ahead and do that. We are going to have negative infinity to 3 pi over 4, 3 pi over 4 to 7 pi over 4, and 7 pi over 4 to infinity. Now our test values are going to be pi over 2 for negative infinity to 3 pi over 4, 3 pi over 2 for 3 pi over 4 to 7 pi over 4, and 11 pi over 6 for 7 pi over 4 to infinity. Now we have to go ahead and test those values. So f double prime of pi over 2, when you plug it into your second derivative, which we know was negative sine x minus cosine x, we're going to get negative 1. Therefore, we can see that f double prime of x is going to be less than 0. When we plug in 3 pi over 2 to our second derivative, we get positive 1. Therefore, we can conclude that the second derivative is greater than 0. And when we plug in 11 pi over 6, we don't even have to finish solving, because we know that we're going to get a negative answer. Therefore, the second derivative is going to be less than 0. Now with these, we can conclude that on the interval of negative pi to 3 pi over 4, the graph is going to be concave down. From 3 pi over 4 to 7 pi over 4, it's going to be concave up. And from 7 pi over 4 to infinity, it's gonna be concave down. Because the concavity of the graph changes on all three intervals, we can determine that both of our x's are actually going to be points of inflection. So 3 pi over 4 and 7 pi over 4 are going to be points of inflection. Our fourth and final step is going to be to go ahead and plug in our x's back into our original function. So f of x is equal to sine x plus cosine x. When we plug in 3 pi over 4, we're going to get radical 2 over 2 minus radical 2 over 2, which is just 0. So 3 pi over 4, comma 0 is going to be a point of inflection. Now we plug in 7 pi over 4 to the original function, and we're going to get negative radical 2 over 2 plus radical 2 over 2, which is also 0. So 7 pi over 4, comma 0 is going to be our second point of inflection.